Hello and welcome back. So we will in this video continue our discussion of this new algorithm that we are trying to develop for unsupervised learning, where we were trying to find a line that, given a data set, minimizes the sum of the lengths of the projections onto this line. But when we did that, we came up with a lot of questions. For example, we started with an error minimization problem and we posed it as an equivalent maximization problem of a particular objective. We wanted to understand that in detail. So the second question is, we came up with a possible algorithm where we find iteratively multiple lines, and then we wanted to know how many rounds should we run this procedure for. Right? So when should we stop this procedure? That was the second question. And more fundamentally, we were trying to understand where is really the compression happening and what are the representations that we are really learning in this problem. What we will do in this video is try to answer some of these questions, and so that the algorithm that we are trying to develop kind of solidifies, and then we have a solid algorithm in place. So we'll start today with where we were last time. So we had a data set. Let's call this x1, x2, xn as usual, where the data points are in d dimension, and we have a vector w1 that we are able to find for this data set, which is argmax over w, such that norm w squared equals 1, w transpose cw. When I say argmax, it is the argument that maximizes the subjective function, and which means specifically the w that maximizes the subjective function. C here was just 1 over n sum over I equals 1 to n xi transpose. So once you find this w1 by the best line that kind of minimizes the error or maximizes this quantity, what we then said was we would compute this new data set where the point x1 becomes x1 tilde, which is just x1 minus its projection onto this w1 multiplied by w1. x2 tilde would be x2 minus the projection of x2 on the first line multiplied by w1, and so on, and xn prime or tilde, not tilde, in this case it's prime, so I mean I'm just called it tilde, it should be prime, xn transpose w1 into w1. So we have this as our new data set. So these set of points form our new data set now. Remember, all these points are still in Rd, just that they are the error vectors in d dimension, right? So now what would our w2 be? Our w2 would be the argmax over w, such that norm w squared equals 1, w transpose C prime transpose w, where C prime is now the matrix, d cross d matrix that you compute out of these error vectors, which would simply be 1 over n sum over I equals 1 to n xi prime transpose, right? So this would be the new matrix. So now you have two lines, right? So the first line was w1, which was the best line that minimized error with respect to the data set. Now you took the error vectors and found the second line, which is w2. Now a natural question arises, well, we have two lines now, can we say anything about the relation between these two lines, right? So natural question is the following: what can we say about w1 and w2? Right. So in particular, is there any specific relationship that exists between these two directions, right? So let's look at it geometrically, right? So we have a bunch of data points. As usual, the data set, let's say, is centered, and now let's say this was our, let me erase this point. I mean, it can fall on the line, doesn't matter. But let's say, to show it clearly, yeah, so let's say this was the best line w1, right? So w1 is somewhere here, remember. So w1 is unit length, so it would be the direction that would point along the I mean in the unit circle. Now, what are the error vectors? Well, if this is x1, this is our error vector. This point is x1 transpose w1 into w1, which means this error vector, which is actually somewhere pointing this, is the remaining piece, which is x1 minus x1 transpose w1 into w1. Okay, so it is pointing in this direction. Let us take one more error vector, which is perhaps this error vector, which is this vector. Maybe this point is x2, this point is x2 transpose w1 into w1. So, this error vector is here, and this point is x2 transpose w1 into w1, and so on, right. So, now as you can observe that these error vectors all line up in the same line. Now, why should that be the case? That should simply be the case because all these error vectors are perpendicular to the original line that we created. That is because of the nature of projections here, right. So, the projections are all perpendicular, these are all perpendicular, and so if I just create a data set which only has the error vectors, that will be on the line perpendicular to the original line that we found, right. So, in 2 dimension. In higher dimensions, it will be in some hyperplane which is perpendicular to the original line that we found, but in 2 dimension there are only 2 perpendicular lines possible. So, it will be on a line. So, now if we find W2 which best fits these error vectors, and because of the fact that the error vectors are all lining up along a line, the best line would exactly be the line where they line up along, right. So, because if I pick any other line, I am going to suffer some extra error which I can avoid by picking W2 as the line, which is exactly the line where these error vectors are falling on, which is the line perpendicular to W1, right. So, which means the observation, again I did not prove this, but then the observation is that all errors, or let us call them residues, are orthogonal to W1, and this implies any line which minimizes sum of errors with respect to residues must also be orthogonal to W1. This needs proof, it is not too hard. I am not going to do this, but then try to argue why this is true yourself. If you are not already seeing it, this is a good place to pause and think about why this must be true, right. So, we will not prove this formally, but then it is not too hard to do this. So, what are we essentially saying, right. So, the implication is that the conclusion is that W2 transpose W1 is 0, right. So, that is what it means to say that W2 is orthogonal to W1, which means my W2 is actually going to be just, you know, something this vector, well not that vector, it has to be by our definition it has to be unit length. So, it will be this vector, this would be W2. Well, it could be in the opposite direction also, that is also fine. So, that would also be a valid unit vector, but then nevertheless that does not violate the orthogonality property at least, right. So, the orthogonality still holds for W1 and W2. Okay. So, now what happens if we continue this procedure, right. So, in 2 dimension, well, you have to stop here because after 2 lines you have kind of found 2 lines such that the residue of the residue is just the 0 vector, right. So, because this line exactly fits the data, so there is no residue anymore. But then if your data point was in 100 dimension, then you do not have to necessarily stop after 2 rounds. You can still continue this procedure, and you might get residue of the residue, residue of the residue of the residue, and so on. And as we keep fitting lines, what we would observe is that we would get a bunch of lines W1, W2, dot dot dot, let us say WD, right. So, in RD, by continuing this procedure, by continuing this procedure, we get W1 to WD with the property, right, that W norm of Wk squared is 1 for all k and Wi transpose Wj equals 0 for all I not equals j. When basically you get W3 which is orthogonal to both W1 and W2, W4 which is orthogonal to all the previous ones, and so on. So, basically what we have ended up getting is a set of orthonormal vectors. Well, orthonormal is just a set of vectors which are mutually perpendicular and of length 1, right. So, that is the orthonormal vectors. Okay. So, this is good. Now, just to understand what is the use of this orthonormal vectors, let's understand this a little bit in a different way, to explicitly computing the residue after round 1, right. So, we know the residue after round 1 is the set or the data set that is used to compute W2 is of this form, right. So, x1 minus x1 transpose W1 into W1 dot 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 xn minus xn transpose W1 into W1, right. So, for where everything is in RD, right. So, all vectors in RD, those are the error vectors. Now, from this we find W2 and we know W1 transpose W2 is 0, right. So, this is the best line that fits residues. Fine, that is good. Now, we have two W's. Now, let us say we go ahead and compute the residues after round 2 just to see what is happening, right. So, it's maybe some of you are already seeing it, but let us try to compute this explicitly. Now, what would be the residues after round 2? Well, from round 1's data set, which was this data set, we computed W2 and then we take the residue of each of this data point with respect to W2, which means that we have to take this data point, subtract it out from its dot product with respect to W2, right. So, which means the first data point would be, well, this was the data point which was x1 minus x1 transpose W1 into W1. Now, this was my original data point. I subtract out its dot product with W2, the same vector transpose W2. This is the scaling factor with respect to W2, right. So, this is what I subtract out and then I do this for every vector. Let us focus on one point to see what comes out. Now, what is this? So, this is just, let me try to simplify this, x1 minus x1 transpose W1 into W1 minus, well, this is x1 transpose W2 minus x1 transpose W1 into W1 transpose W2 into W2 dot dot dot, which is exactly x1 minus x1 transpose W1 into W1 minus, well, the first term is x1 transpose W2 into W2, but now we notice that because of the fact whatever we argued earlier that W1 and W2 are orthogonal, this value is 0, which means that this second term is 0, right. So, which means this would be our first data point and so on, right. So, after round 2 we observe that the residue is x1 minus, well, x1's projection onto W1, subtract out the x1's projection onto W2. Now, if we continue this after d rounds, again this needs an argument, but then it should not be too hard to see that residues after d rounds, what would be the residue? Well, it would be for all I, the residue xi would be xi minus, well, xi transpose W1 into W1 plus xi transpose W2 into W2 plus dot 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 plus xi transpose WD into WD. Now, what do you think should be the residue after d rounds, right? So, I am in d dimension, all the data points are in d dimension and I run this algorithm d times and then I look at the residue. What do you think would be the residue after d rounds? Well, in two dimensional case it was very obvious, right. So, you had an initial set of data points, you found a line, well, or you found the projections and the error vectors with respect to the best line, all the error vectors lined up. So, the second line exactly fit the data set. So, the residue after round 2 would just be the set of all 0 vectors, because the second vector exactly fit the data points, all the vectors are lined up. Now, the same thing would happen in d dimension if you run it long enough, right. So, which means if you run it for d rounds. So, after d rounds, all the error vectors would simply become 0 vectors, right. So, because you have kind of removed all the components of this error vector, and there can only be d independent components, which are w1 to wd in this case, right. So, which means all these vectors are actually the 0 vectors after d rounds, right. So, in Rd. Now, that tells us that xi itself is just xi transpose w1 into w1 plus xi transpose w2 into w2 plus dot 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 plus xi transpose wd into wd, right. So, basically what we have done is, again, if you know a bit of linear algebra, you can already see what's happening is that we have expressed our data set, every point in the data set, in a different basis, in a different orthonormal basis, right. So, the x1, x2 till xn were expressed in standard basis. Now, you are expressing the same data set in the basis of w1 to wd, right. So, basically all we have done is doing a change of basis. Fine. So, all these data points can be expressed in any basis which whatsoever, right. So, there is nothing, I mean, the question is what have we gained by doing this, right. So, we could have had the standard basis itself, but then now we are choosing to express all the data points on a different basis, which is the w1 to wd basis. So, what, right. So, the question is what have we gained? What have we gained? Well, the first thing we are gaining is the following, right. So, if our data lives in a low dimensional linear space or subspace, then we do not have to run d rounds, right. So, the residues become 0 much earlier than d rounds, right. So, we keep running this algorithm iteratively, and at some point we realize that the residues have all become 0, then there is no point in continuing further and finding a different line, right. So, because that is not going to add anything more to our information, because all the vectors are 0 vectors. So, what is this telling us? That if it so happens that your data was in low dimensional space, then your algorithm would stop much earlier than running for d rounds. So, why is this a useful thing now, right? So, this is useful because let us take an example and see why this is a useful thing, right. So, example, say data set that we have is such that after 3 rounds the residues become 0, right. So, you run 3 rounds and then all the error vectors residues become 0, right. So, residues become 0. Now, what does that tell us, right. So, the data set itself initially was in some d dimensional data set, that is the usual data set that we have, x1 to xn, and data points all xi are in Rd. Now, what does it mean to say the residues become 0 after 3 rounds? It means that there exists, we have found w1, w2, w3 such that for all I, xi equals xi transpose w1 into w1 plus xi transpose w2 into w2 plus xi transpose w3 into w3. Now, where are these w1, w2, w3? Well, w1, w2, w3 are the lines that we find for our data sets. So, they are all in R100 or sorry R, well, yeah. So, let us say this is 100 for the moment to make it to give some numbers. Let us say the data set is in all 100 dimension. So, all these 3 w1, w2, w3 are in 100 dimension. That is good, but what are we saying? We are saying that, well, Now, if we have the representatives and the coefficients, so the representatives of course will be W1, W2, W3, which will all three lines are in 100 dimension, but the coefficients, now well, to reconstruct xi we do not need 100 numbers, right. So, we need only 3 numbers per data point, right. So, coefficient for the ith data point, right. So, are just xi transpose W1, xi transpose W2, xi transpose W3. It is just the dot product of the data point with respect to each of these directions that we have found, right. So, which is in R3, just 3 numbers per data point. So, initially we had 100 dimensional data points, n of them. So, we had to do the naive way to store these would be to say that we would have 100 into n numbers that are needed to store. Now, because of the observation that after 3 rounds the residues all become 0, well then it means that for the representative you need 3 into 100, 3 into 100 for W1, W2, W3, plus for each data point you only need 3 points, right. So, which would be just 3 times n, right. So, this is the number of this is the total number of numbers that you need to store or values that you need to store, right. So, instead of I mean in general instead of d times n which you may have to store, now you have to store d times k, where k is the number of rounds after which the residues become 0, plus k times n. For each data point you only have k numbers instead of d numbers, right. So, d into n could be much larger than d times k plus k times n, especially if k is small, right. So, think of n as 100, right. So, then this means that this is 100 into 100, that would be 10,000, whereas this is 3 into 100 plus 3 into 100, which is just 600, right. So, instead of 10,000 we have only managed to store only 600 numbers. Of course, this is assuming that you have the residues become 0 after 3 rounds. Now, what, just to be very sure, so this is data point specific, right. So, every data point, the numbers that we are storing will depend on what the original data point itself, right. So, this is data point specific. The W1, W2 is common for the entire data set, right. So, that is why they are the representative, and then this representation for this data point depends on the representative, but then specific. Now, if we want to reconstruct the data set, we could do that using the representative and coefficients by taking the linear combination of the representatives where the coefficients are specified by these dot products. So, that would give us exact reconstruction in this case. Okay. So, now this is good. Now, the question then is, well, if it so happens that after 3 rounds the residues become exactly 0, we are good, fine, but this may or may not happen in practice, and the relevant question that we should answer in practice is, well, what if data approximately lies in a low dimensional space? What does that mean? That means that for instance, the simplest example is the 2-dimensional space. Again, we might have data like this. Well, there is no single line that fits the data. So, there is no single 1-dimensional space where the data actually lies in, but still we are kind of happy with this line, 1-dimensional representation, which means that we are saying we can tolerate some amount of error, right. So, that number has to be fixed by us. How much tolerance we need should be fixed by us. So, how can we fix this tolerance? What should we look at to decide this tolerance? There are different things that you can look at, and the simplest way to decide on a tolerance would be to do the following, right. So, here let us look at the Pythagoras theorem. Let us take any data point, right. So, let us say look at any data point and look at its length, right. So, maybe some data point xi and then its length. Well, by Pythagoras, this length is the sum of the lengths of its projection onto any line, not just the best line, any line, plus the error vector's length, right. So, length squared, sorry, length squared of xi is the sum of the length squared of the projection onto any fixed line plus the error vector that it suffers with respect to that line, right. So, which means this is xi minus xi transpose w into w squared plus xi transpose w into w squared, right. So, this is true for any data point. Now, this is true for all I, which means so if I just average this left hand side over all I, this, so for any w, right. So, in RD this is true where xi's are all in RD. If I do the averaging here, I get this plus 1 over n sum over I xi transpose w to w squared. Well, for any w in RD, but then we typically care about w such that w's length is 1. The fact is true for any w. Well, if you have any w, then you will have to divide this by the length of w. So, let us fix the length of w to be 1, right. So, that this is true always. Okay. So, now what are we saying? We are saying that, well, for any w, the average length of the data set is equal to the average error that the data set incurs with respect to the w that we have plus this quantity, right. So, which means we want that w such that this quantity is as large as possible. The error should be as small as possible, or this quantity should be as large as possible, which means we can look at this value after we find a w and see what happens to that value, right. So, basically what we can do is we will use the fact that larger the value of the second term, which is norm of xi transpose w squared, right. So, this is a constant that square of it will come out, norm w squared is anyway 1. So, this is essentially sum over I equals 1 to n xi transpose w squared, the better the fit, right. So, this is exactly same as this, both of these are same, okay. Fine. So, now what we can do is do the following, right. So, we will do the following where we will look at rounds as the number of rounds proceeds. Let us call that round k. We will look at the average that we will suffer with respect to wk, the kth rounds value that we find out, right. So, now this is going to be as large as possible for w1, this is for round 1, because you are essentially maximizing this for round 1. And now, whatever you find for round 2 is going to be lesser than this. If it is greater than this, we would have found that in round 1 itself. So, this value is going to go down, right. So, this is going to fall down, and let us say it falls down like this, right. So, now if it falls down like this, there might be an elbow point which is some k, after which these numbers are very, very small. So, what does that essentially tell us? At a high level, that tells us that the top k w's that we have found are actually the signal directions, right. So, that is where the most of the information is, and we will talk about what it means to say information, signal and so on a little bit later. But for now, we understand that, well, if it kind of drops down and becomes really small after a point, these can be thought of as errors, right. So, error directions. So, what we can do is we can kind of use a rule of thumb to say that after a particular value, if the sum of these values is divided by the total sum is greater than some quantity threshold, let us say 95% of the total sum is kind of explained by just the top k, then we will pick only the top k. We will revisit this in a slightly different notation later, that's why I am not writing this down, but the idea should be clear, right. So, as the rounds progresses, we are trying to find the quantity, and then cutting it out at some point where we think enough amount of information has been gained. Of course, that's just a rule of thumb, so we are not like arguing that this particular k is the best k. Unless we make more assumptions about the data, we cannot really do that, but a rule of thumb would be to say that, well, this captures 95% of the total mass that you will have, where you sum this up over all d rounds, right. So, after d rounds, this guy is going to become 0 anyway, right. So, yeah, yeah, okay. So, now let's we have understood the algorithm, right. So, the algorithm is kind of complete now. So, you start with some data set, and then you can center this data set, and then start doing this iterative procedure to get the W's, and after some point, if you feel that the error vectors, so this quantity that you are trying to maximize is too small, or with respect to the total that quantity that you have so far managed to achieve, then you stop there.